When we are looking at whether a column could buckle, the way the ends of the column are attached greatly affects whether it resists buckling or not, whether both ends are fixed in concrete or they're both pinned or what. This chart is a copy out of the AISC steel manual. We'll look at that again momentarily. And after we find the slenderness ratio, then we look at the critical buckling load, you'll recall. So the fact that length squared is in the bottom of this formula means that the buckling load is very sensitive to changes in length. This is not just length in the bottom, it's length times length, length squared. So that means if you make the length twice as long, you'll reduce its capacity, the column's capacity to resist, by 4. If you cut the length of the column in half, you're going to increase the column's capacity by 4. So length makes a big difference. And I'm just going to quickly run through an example to illustrate what we mean. Let's say you have a column that's 10 feet long, and that means it's 120 inches long. 10 times 12 is 120 inches. So let's run through figuring out the critical buckling load for that 120-inch long column. If it's 120 inches, then we have 120 squared in the bottom of our formula. Blah, blah, blah. Pi squared is about 9.87, and there's some number. Okay, anyway, there's some number if the thing is 10 feet long, or 120 inches. What if we double the length of the column? We make it 20 feet long, or 240 inches. Now if I plug those numbers in, 240 squared in the bottom of this formula, da-da-da, da-da-da, so what? Now I'm going to plug in a hypothetical E and I. So let's say this is a steel wide flange, 8 by 31. That means the modulus of elasticity, E, is 29 million, and the moment of inertia is 37.1. So now if we plug those, E and I, into this formula, we find out that if the thing is 10 feet long, blah, 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 we get a critical buckling load of over 737,000 pounds. If the thing is 20 feet long, blah, 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 we get a critical buckling load of 184,000 pounds. Look at the difference. When you double the length of this column, it takes far less load to cause the thing to buckle. The length makes a big difference. 2 times the length gives us about a quarter of the buckling load that it would take to cause the thing to fail. So what? Well, here's our chart from AISC again. And what they are telling us is we are looking for, okay, how long is the actual length of the column that is really going to be buckling? And we are looking for something called the K value. It's just a coefficient. We'll multiply K times the length to get the effective length. So, for example, if you have a column which is pinned at both ends, as we see here, here are some other examples at the bottom, pinned connections, then the effective length is the length, so the K factor is just 1. If the column is 16 feet long, the effective length is 16 feet long. There you go. Or as our book says, here's his picture. But now, what if you had the column fixed at one end? Maybe you cast the bottom end of the thing in concrete. So as the thing starts flexing, it does not really start flexing until partway up the column. And the length of the thing that will actually do the buckling turns out to be only 0.7 of the entire length. In other words, the K factor is 0.7. And this could be true if the bottom end is fixed, as you see in the lower left, or if the top end is fixed, as you see in the lower right picture. In either case, if one end is pinned and one end is fixed, the K factor that you use for the length is 0.7 of the original length. And what this tells us is you'll be doing yourself a favor if you fix one end, because then it will be, the slenderness ratio will change and it'll be less likely to buckle. Here's our book talking about that. So if one end is fixed and one end is pinned, the K factor is 0.7. And if you look at our P crit, our critical buckling load, the length in the bottom of our P crit formula is going to be only 0.7 the original length. So let's see what that means with some example. Here we have a wood pole. It's 8 inches in diameter, and it is pinned at the top end and fixed at the bottom end. This timber pole has a modulus of elasticity of 1,000,000 psi, and we have a load of 25,000 pounds coming down on top of it. Let's find what height of pole could we use that would still support that load without buckling. So this is a little bit more sophisticated, I think. We've got this information. We're trying to find out how long can we make that pole safely. Here's our P crit formula, critical buckling load. And we already know modulus of elasticity, it's 1,000,000. We still need to find moment of inertia. So let's turn to our next handout. The shapes. This is a table out of our book where he's showing how you could calculate the moment of inertia by yourself for a rectangle or a triangle or a circle or a donut or whatever. So the moment of inertia for a circular shape, he gives us two different versions we could choose from, one using radius to the fourth and the other using diameter to the fourth. Well, I feel like we're given the diameter, so let's just use the version which has diameter in it. I always feel like each time you convert something is one more opportunity to make a mistake, and the simpler you can keep things, you're just reducing the chances that you'll punch the wrong button. So if he gives us the diameter, let's use the diameter version. And so the moment of inertia, using that formula there, pi d fourth over 64 is pi times 8 to the fourth over 64. Now be careful here. Be very, very careful. You do not want to go pi times 8, yay, and then take that whole thing to the fourth. That will give you a giant number. You want 8 to the fourth, and then multiply that times pi, and then divide that by 64. And you'll get a number just a little bit bigger than 201. And if you look at the notes field in these PowerPoint slides, you'll see I leave a message for you saying it's a tiny bit bigger than 201. We're going to round to 201. Okay, now the pole is pinned at one end and fixed at one end. So what is the K factor? Looking at our chart from AISC, the K factor is 0.7, isn't it? So now what do we know? We know the modulus of elasticity, the moment of inertia, the load, and the k-factor. The k-factor of 0.7 means the length that you're working with is going to be 0.7 of the length. P crit is 25,000 pounds, so here I've plugged in all these numbers. And we're looking for length, so let's use our handy-dandy trick of swapping the term that's by itself with the term on the bottom. So we'll move the 25,000 to the bottom of the fraction, and we'll move the 0.7L squared out here by itself. And now we'll continue these numbers on the next slide. So here's how far we've gotten so far. Here's our formula with 0.7L squared equals all this glop. And all this glop is a little over 79,000. All right, and we're trying to find L, but we've got a squared in there. How do you get to 0.7L from squared? You take the square root, don't you? And if you do the same thing to both sides are still equal. So let's take the square root of both sides. All right, that takes us to the square root of this is 0.7L. The square root of this is 281.694. All right, we're looking for L. What is our length? So let's divide both sides by 0.7. That'll get the 0.7 out of there. So those 0.7s cancel out. We wind up with L equals this, which is 402.42 inches. Remember, we had converted our length to inches, so this is in inches. So that is the maximum length that can support this load without buckling. Now, if you wanted to convert this to feet, and I would imagine you would, how do you do that? If this is 402.42 inches, that divided by 12 will give you around 33.5 feet. And if you're ordering a big old 8-inch pole, if you go to the lumber yard and say, give me 402 inches, they'll go, I don't know. My tape doesn't go that big. But if you say, give me 33.5 feet, they go, oh yeah, I can do that. So we're going with 33.53 feet.